Hello, and welcome back to Sensors and Sensor Systems. Today's mini lecture is on a form of device-to-device communication protocol called the Inter-Integrated Circuit Protocol, or I2C. The I2C protocol allows communication between multiple controllers and multiple workers. In a sensing system, this likely means multiple microcontrollers talking to multiple sensors. Like the UART communication protocol, messages are broken up into frames of data. Each message has an address frame that contains the unique binary address of one of the workers, and the message also contains one or more data frames that contain the data being transmitted. The message also includes start and stop conditions, which are well defined for I2C, a read or write bit that indicates whether data is being read from a worker or written to a worker, and acknowledge bits that allow the worker to indicate that it successfully received or transmitted information. So let's take a look at how this works. The first step is that we'll go through the write condition that is initiated by the SDA signal first going from high to low, and then the SCL signal going from high to low. And note in these timing diagrams, time is going from right to left rather than from left to right, which is what we may be more used to. After we've indicated that the start condition has happened, the next thing that's going to happen is that SCL is going to take over the role of clock in the system. And we see that in the next slide here. Time still going from right to left. The next thing that happens is on the SDA line, we're now going to send from the controller to all the workers an address. And that address is going to correspond only to one of those workers. In this case, our address, again time going from right to left, reading from right to left, is going to be 0101101, which indicates that worker number 3 is going to be involved in the communication of this message. Since the read-write bit is low, that indicates that we're going to have a write operation and that the controller is going to be sending information to worker 3. Now once this address frame is transmitted, workers number 2 and number 1 just ignore what's going on both the SDA and SCL lines. After we've sent the address, what happens is worker 3 will now bring the SDA line low for 1 bit to acknowledge that it has received the address line from the controller and is ready to communicate with the controller uniquely. The controller will now send data, in this case an 8-bit data frame, to or from the designated worker. Since we're in the write condition, as indicated by the write bit being low on the previous slide, the controller is now going to send information to worker number 3. Again, time going from right to left here means that the information that's being sent, as shown here, is going to be 1, 0, 1, 1, 0, 1, 0, 0. And that's the information or the data that is now going from controller to worker number 3. After that's been done and acknowledged, again, the worker is going to take the SDA line low to indicate that the write operation of those 8 bits has been completed successfully. Now one thing to note is, going back to this slide, once we finish transferring all our data frames, recall now that in the original message, once we've acknowledged that final 8 bits, we also have to now engage the stop condition, which will involve the SDA line now going low to high followed by the SCL line switching from low to high, exactly the opposite of what the start condition was. Once that occurs, the communication is complete, and the controller can now initiate communication with another worker. Now, one thing that's a little bit tricky about I2C is that it defaults both lines, SDA and SCL, default high. And that's because we have to connect pull-up resistors from both SCL and SDA lines to the power supply, VCC. That guarantees that their default state is high, and if we want the lines to go low, we have to force them low. But they'll never go high unless we put these pull-up resistors in here to guarantee the default state. So the pros of the I2C protocol is that we only need 2 wires. We are allowing for multiple controllers and multiple workers, previously called masters and slaves, respectively. And the acknowledge bit is a confirmation that each data frame has been transferred successfully. The downside is that our data packets are limited to only 8 bits. This is a pretty complicated communication protocol, and it's slower than other common communication protocols like SPI. And while I2C is the most complicated among UART, SPI, and I2C protocols, it also allows for great versatility in communication. It allows us to have multiple microcontrollers or other controllers in the system and a wide variety of sensors in the system, and it allows communication to occur among them. And for this reason, it's really valuable for more complicated sensor networks. So this concludes our very brief introduction of the I2C protocol. Thanks for joining us, and we hope you'll join us again soon.